Welcome back. This is Topic 29, Training in Practice. Epochs, mini batches, and optimizers. Every training loop we have written so far quietly made a handful of choices for us. Today, we finally name those choices and see how each one changed the result. 4 parts. First, the vocabulary, epoch, batch, and iteration. Second, batch versus stochastic versus mini-batch gradient descent. Third, how many epochs and what batch size to use. And fourth, the optimizers, plain SGT, momentum, and Atom. Start with a confession. Every training loop so far quietly made 3 decisions without discussing them. The first, it used all of the data for every single gradient step. The second, it repeated the loop some fixed number of epochs, and we never asked how many was right. And the third, it stepped with plain SGD, except the time we switched to something called Atom, and simply said, it was smarter, without saying why. Here is the framing for the whole topic. None of this changes the math of gradient descent. These are the knobs around it. And every real training run turns all of them. 3 counting words cover everything. The first is epoch. An epoch is one full pass over the training set. Every sample seen exactly once. The second is batch. A batch is the group of samples used for one gradient update. And the third is iteration. An iteration is one update, that is, one batch process. Epoch, batch, iteration. Put numbers on it. With 1000 samples and a batch size of 100, one epoch is 10 iterations. 10 batches of 110 updates, one pass. Let us count it out on a real dataset. 60,000 training images. Batch size 100. One epoch splits into 60,000 divided by 100, which is 600 iterations. Now train for 10 epochs. The weights are updated 600 times per epoch, times 10 epochs, which is 6,000 updates in total. Sit with that. The same data is seen just 10 times, but the network takes 6,000 separate steps downhill. That gap between passes over the data and updates actually made is the whole point of the next section. Here is one epoch as a picture. The shuffle training set is cut into batches. Each batch drives one gradient update, one iteration. Work through every batch and you have completed one epoch. Now the confession about our own code. Every loop we ever wrote for epoch in range of 2000 fed the whole dataset to each update. So each thing we called epoch was exactly one iteration of full batch gradient descent. One update per pass. And that is just one extreme of a spectrum. Let us see the whole spectrum. The gradient formula averages over samples, but over which samples? Three answers. First, batch gradient descent, average over all n samples. Each step is the exact gradient, so the path is smooth and stable, but you pay for the entire dataset just to move once. Second, stochastic gradient descent, or SGD, use just one sample per update. Each step is nearly free, and there are n of them per epoch, but each gradient is a noisy estimate, so the path staggers like a walker heading downhill in the dark. Third, mini-batch gradient descent, the compromise everyone actually uses. Average over a small batch, say 32. Most of the noise averages out. The steps stay cheap and frequent, and the batch is one GPU-friendly matrix operation. Let us watch the difference. On the left, cost against the number of updates. All three follow roughly the same curve per update. But remember what an update costs. Batch pays 1000 samples a step. SGD pays 1. On the right, the pass in wait space. Batch in blue glides smoothly to the star. SGD in red wobbles violently and keeps jittering around the minimum without settling. Mini batch in green is the sensible middle. After one full epoch, the scoreboard is stuck. Batch gradient descent has taken just one update, and its cost is still about 31. Mini batch with batch size 32 has taken 32 updates in that same epoch, and it already sits at a cost of about 1.1, essentially converged. Same data, same arithmetic. Mini batching just spends it in smaller, more frequent steps, and it outprogressed batch gradient descent by about 30 times in a single epoch. Let us make that concrete. One epoch is one pass over all 60,000 samples. The question is, how many weight updates that one pass actually makes? Whole batch gradient descent uses all 60,000 at once, so it makes exactly one update. Mini batch with a batch size of 100 makes 60,000 divided by 100, which is 600 updates in that same pace. And SGD, one sample at a time, makes 60,000 updates in the very same pass. The same pass over the data, sliced 3 ways, buys one step 600 steps, or 60,000. More cheaper steps is exactly why mini batch wins. Now, how many epochs and what batch size? Both knobs answer to the same experiment: train and watch the curves. On the left, train and test accuracy against epochs. On the right, cost per epoch for several batch sizes. Read the left first. Accuracy climbs steeply for the first 50 epochs or so, then plateaus near 100. After that, more epochs by nothing, and on harder problems, they can actually hurt as the network starts memorizing the training set. That is overfitting, and we catch it by watching the test curve not the training curve. Now the right plot, small batches make more updates per epoch, so they reach the floor in 1 or 2 epochs, while full batch is still descending after 15. But there's a trade-off hiding in that plot. Tiny batches like 8 are noisier and waste the GPU's parallelism. Huge batches are smooth but slow per epoch. Powers of 2 in the 32 to 256 range are the everyday default. The last knob is how to use the gradient once you have it. Plain SGD is exactly our update rule. W moves by minus alpha times the gradient. Two upgrades matter. The first is momentum. Momentum gives the update. Inertia, the new velocity is beta times the old velocity plus the gradient, and we step along that velocity with beta typically 0.9. Like a heavy ball rolling downhill, it plows through small bumps and accelerates along directions that keep pointing the same way. The second upgrade is Atom. Atom keeps a running average of each parameter's gradient, which is the momentum idea, and also of its squared gradient. It uses that second quantity to give every parameter its own effective learning rate. In practice, Atom is the JustWorks default. Here is the payoff. Same network, same 2 moons data, same number of epochs, and only the optimizer changes. After 300 epochs, plain SGD is still at a loss of 0.29, that is 88% accuracy. Momentum has pushed to 0.036, 98%. And Atom reaches 0.018, 99%. None of them changed the model or the data, only the stepping strategy. Let us work one momentum update by hand. Take beta equal to 0.9, a learning rate alpha of 0.1, and suppose the gradient is a steady 2 straight down a long slope. Start from rest, velocity 0. Step 1. Velocity is 0.9 times 0 plus 2, which is 2. The wait step is alpha times velocity, 0.2. Step 2. Velocity is 0.9 times 2 plus 2, which is 3.8. The wait step grows to 0.38. Step 3. Velocity is 0.9 times 3.8 plus 2, which is 5.42. The wait step is now 0.542. Watch what happens. The velocity accumulates. Plain SGT would take a flat step of 0.2 every single time. Momentum keeps speeding up along the same direction. So how fast can it go? With the steady gradient, the velocity does not grow forever. It settles where the 0.9 carryover balances the fresh gradient. That limit is the gradient over 1 minus beta, which is 2 over 1 minus 0.9. That is 2 over 0.1, which equals 20. So the top step is alpha times 20, which is 0.1 times 20 equal to 2. That is 10 times the first step of 0.2. The factor 1 over 1 minus beta, which is 10 here, is the inertia multiplier. Down a consistent slope, momentum ends up moving about 10 times faster than plane SGD. That is exactly why it powers through the long, narrow ravines that stall the plane method. Now, what does Adam add? In plain English, momentum smooths which way to go. Adam also adapts how big each parameter's step is. First, it tracks each parameter's recent squared gradient, a running sense of how big that parameter's gradients have been. Second, it uses that to scale the steps. Parameters with consistently big gradients get gentler steps. Really updated ones get bolder steps. The net effect is that every parameter gets its own effective learning rate tuned on the fly. And there is no heavy math to run it, just one line of code. This is precisely why we reached for Adam when playing SGD stalled on XOR back in Topic 25. It adapts where a single fixed step size gets stuck. In code, the whole choice is one line. Plane gradient descent is optim.scgd with a learning rate. Add inertia by passing momentum equal to 0.9 or switch to optim.atom for adaptive per parameter steps. One honest caveat. Atom is the best default, not always the best final answer. Well-tuned SGD with momentum still wins some benchmarks, and every optimizer still needs a sensible learning rate. So, what do you actually reach for? Batch size, a power of 2 in the 32 to 256 range. Epochs watch the train and test curves and stop when they plateau before the test curve turns back up. Optimizer, reach for Atom first and try well-tuned SGD with momentum when you are chasing the last bit of accuracy. That combination, a data loader with a batch size plus optim.atom, is the exact pattern MNIST uses in the next topic. Let us recap. Epoch is one pass over the data, batch is the samples in one update, and iteration is one update. Batch size 100 on 1000 samples gives 10 iterations per epoch. Batch gradient descent is smooth but expensive. SGD is cheap but noisy and jitters at the minimum. Many batch is the standard, nearly as smooth as batch, nearly as cheap as SGD, and GPU friendly. Choose the number of epochs by watching the curves plateau and mine overfitting. Choose the batch size in the tens to hundreds, where smaller means more updates per epoch. And the optimizers, momentum adds inertia, Adam adds per parameter adaptive steps. The identical model and data went from 88% to 98 to 99% just by changing the optimizer. That is the topic. See you next time for MNIST.